Hello, and thank you for watching my BCCE 2022 talk. My name is DeSutter, and I did my PhD in the Learning Sciences in the STIFE group at UIC. Now I'm at Catalyst Education and part of the team working on developing the Labflow product. I've been driving the thinking around how we can accelerate research both at Catalyst and in the broader DBER community into student learning in laboratory. What we'll be looking at today is the first phase of this effort. I'm looking forward to having an open discussion with the community as we evolve this approach. The teaching laboratory is a ubiquitous component of the STEM education track. This is in part because of the normative stance we've taken in many university science departments, that it is critical to get students familiar with doing science in addition to a purely theoretical introduction. However, there has been a long-standing concern that the evidence for the efficacy of labs is sparse. This concern has prompted robust research and discussion in the literature around what purpose labs should serve in broader STEM education. While it's clear that a scientist must have a well-integrated understanding of the theory in order to do science, there are diverging views on whether this should be the chief purpose of labs early in a student's science education. This has led to calls for a careful reconsideration of what learning means in the laboratory and what we should take as evidence of learning. When considering what learning means in lab, we can't ignore the fact that labs foreground the practical skills of science in a way that is not experienced in other coursework. A number of surveys of undergraduate faculty have identified commonly held beliefs about the goals of lab and the skills that students should become familiar with, which include engaging the scientific process, developing critical thinking and communication skills, and becoming adept at various laboratory and equipment techniques. Even though all of these skills are vital for students to acquire, in this talk I will talk narrowly about assessing a subset of these practical skills, laboratory techniques. Laboratory techniques are what Bretz and colleagues refer to as fitting within the psychomotor domain and have to do with the manipulation of equipment in carrying out specific experimental processes. So how do we go about assessing laboratory techniques as I've defined? Broadly speaking, the assessment of laboratory techniques falls into two categories. We can either assess a student's ability to execute a skill by looking at the outputs of their work. How much compound were they able to recover? What was the purity of their product? The second category involves directly assessing those skills with lab practicals, where a student can demonstrate what they know to an external examiner. While useful, both of these approaches have some well-known limitations. In the first case, where we only look at the quality of output, we can really only infer students' understanding of the underlying techniques, and we may either over or underestimate their actual skill. Direct observation, which is much closer to the actual assessment target, relies on a subjective evaluation from an instructor, which may be prone to individual bias. Direct observation is also a big undertaking. It means either only observing a subset of students on a regular basis, or only having comprehensive examinations at a few time points within a course. While prior assessment methods have proved very useful, there may be untapped potential in data captured about students' laboratory techniques in large-scale data on platforms like Labflow, where data is consistent, has high temporal resolution, and contains a lot of process information. In an effort to make sure we were taking a principled approach to looking at data in Labflow, I first sought out an assessment framework for the lab skills from the ChemEd research community, and have decided to apply a similar evidence-centered design paradigm advocated by Zhang and Wink in their recent paper. Briefly, their approach uses a set of multi-dimensional learning statements built in the language of disciplinary core ideas taken from the Anchoring Concepts Content Map, or ACCM, and the Science and Engineering Practices and Cross-Cutting Concepts from the Next Generation Science Standards. The constructs that appear in the multidimensional learning statements are used to write out a series of learning performances. Learning performances are the actions that a student should be able to exhibit when having learned a particular lab skill. These learning performances are broken down into one, or in many cases, multiple evidence statements. These evidence statements get us to put down explicitly what we take as evidence of a student knowing a lab skill. And the final piece is to explicitly identify the tasks or contexts where we will find each piece of evidence. This research study was motivated by the following research question. What does applying an evidence-centered design approach to large-scale laboratory learning data reveal about the nature of students' existing and emerging laboratory techniques in general chemistry? In particular, what component skills comprise broader notions of a laboratory technique? How can we define the components of these techniques at a microgenetic level? And what differences emerge when looking at students' reported data versus the full process they went through to collect and record that data? In this study, I want to present a first look at where we're at in trying to assess the lab skill accurately reading glassware using big data at Labflow. We will see a lot of data during this talk, and this data is generated in a way that is specific to how Labflow operates. So I want to walk us through the data and how I analyzed it to derive metrics that were aligned to the assessment framework. For the purposes of this study, I selected one of the Open Education OER labs from Labflow's library of experiments. I specifically selected the Glassware, Techniques, and Measurements report because it is our most popular OER report. It also has very specific activities that provide good context for understanding reading glassware. This lab report is widely used. It has been used to date in over 80 courses, and a total of 8,136 students have completed this experiment, with over 1.5 million unique records spanning all of the item-level attempts that those students generated. Note that for the purposes of today's analysis, we will only be focusing on students who completed this experiment in person in the laboratory. Data for this analysis was collected under normal educational use of Labflow and governed by Labflow's terms of service. Let's look briefly at the procedure for the Glassware, Techniques, and Measurements report. This report is broken down into two parts. The first part asks students to use 5 trials to determine the density of an unknown liquid. They take 10 milliliter samples of that liquid using a 10 milliliter graduated cylinder. They then calculate the mass of the liquid by subtracting the mass of the glassware, and use the relationship of mass to volume to estimate the density. They then take the trial density estimates and compute both an average density of the unknown liquid and a percent error of the density estimate relative to a reference density. Students then repeat the same exercise in the second half of the procedure using water. The main difference here is that all volume measurements are taken with a burette and can vary between 3 and 5 milliliters per trial. If you'd like to explore this activity in more detail, please follow the link on the right at links.labflow.com/gm. All responses were collected through a Labflow report. Reports are versatile modules that can be customized to support most data collection and analysis for any experiment. Students enter data as they progress through the procedure and receive feedback about their recorded measurements. There are 2 primary points where a student receives feedback during data entry. The first is when entering a measurement. Each measurement is checked against rules associated with each data entry prompt. Depending on the procedure, this might include checking for the correct number of decimal places or significant digits. Here we can see 2 students entering a mass value that is specified to 2 instead of 4 decimal places. Students can only progress when Labflow determines that the value that they've entered does not conflict with one of these rules. The second time students receive feedback is when they submit their dataset. Reports can be configured to perform a holistic integrity check before accepting the data. This prevents bad data from moving through to the analysis. Common things we might try to catch include making sure that volumes and masses are positive quantities, and that students haven't switched around initial and final volumes. Although students must enter a value that is accepted by the system in order to proceed, Labflow maintains a historic trace of the measurements that a student entered before the final value was accepted. Here we can see a student who has entered multiple volumes to an incorrect precision before finally having 10.01 milliliters accepted as their trial 1 volume. Trace data like this can serve as a useful window into students' thinking as they progress through a data recording activity. To analyze this data, I constructed learning performances for the lab skill of accurately reading glassware, and identified specific evidence statements aligned to the type of data we collected from students in Labflow. I then used targeted queries to tag this data for the presence or absence of these pieces of evidence. Competence thresholds were defined so that a student could be coded for an evidence statement if their data entry was consistent with that evidence statement across all experimental trials for a piece of glassware. If students were coded as exhibiting all evidence statements within a learning performance, they then were coded as exhibiting that learning performance. This analysis was carried out separately on 2 subsets of data for each student. The first analysis was only on the final value that they submitted and was accepted by Labflow. The second analysis included the totality of the trace of attempts that students made, including that final value. Briefly, here are the learning performances and their related evidence statements. The first learning performance focuses on whether students could report volumes for multiple types of glassware. The second learning performance focused on specifically whether the data students entered was in the appropriate range of the glassware and whether it was given to the correct precision. The detailed evidence statements are presented to the right and articulate how the final accepted value and trace data were used to find evidence of each learning performance. To give you a sense of what the data looked like in this analysis, take a representative sample of a student entering volume values for a graduated cylinder trial. The entire trace of the student's data entry is presented in tabular form in chronological order, from the first attempt that the student entered to the accepted value. The data were cleaned to remove any duplicate records from the dataset. This was most common when a student would try to submit a value multiple times in a row without addressing the feedback prompt that they were given, like the incorrect number of decimal places in their value. Once we removed duplicate values, we were only left with the unique attempts that a student made for each measurement during data entry. The cleaned up data was then tagged with codes defined from each learning performance. For example, attempts were tagged to identify whether they were valid and numeric, in the range of the specific glassware, and how many decimal places were present. The data traces for each measurement were then coded to identify how the student modified the value during attempts. Using the number of decimal places, we could tag whether the precision went up or down between sequential attempts. In cases where the student changed the value and precision simultaneously by more than the gap in the precision alone, those were tagged as precision and value changes. The codes were then turned into a string representation, and each string representation was tagged for the modification type that occurred most frequently within that string as its primary strategy. Data entry traces were then summarized for each measurement in the procedure. Additional codes as well as computed values were added at the level of aggregation, like how many attempts the student made entering the value, the absolute spread of the values from min to max, how they changed the precision of the value and how many times they did so, and what their primary strategy was for arriving at an accepted value. With that in mind, let's take a look at our initial attempt to assess whether students were successful at accurately reading glassware. This first analysis looks at Learning Performance 1. The evidence statement for this learning performance indicates that students should be able to record volumes for multiple types of glassware for all trials. When looking at whether their accepted value was a valid numeric input, we see that 100% of students attained this benchmark. Because Labflow only allows data to be accepted if it's a valid numeric input, this is consistent that 100% of students were able to do this for both graduated cylinders and burette trials. For convenience throughout this analysis, I've printed the learning performance, evidence statement, and data sources at the top of each slide. When we apply a similar competence threshold to the entirety of the trace of their data entry attempts, we can see that students still overwhelmingly entered valid volume measurements. Less than 2% of students attempted to either leave values blank or filled in non-numeric responses. The second component of this evidence statement specifies that students should make fewer attempts to enter volume measurements across trials. Here we can see the average number of attempts students took to get a volume value accepted in their trace data entry. The plot shows a rapid reduction in the number of attempts students required. The number of attempts goes down as students move from the graduated cylinder to burette measurements later on in the procedure. 80% of students showed a similar declining error reduction pattern across graduated cylinder trials, but only 66% of them did so for burette trials. Let's look at a quick summary then of the first learning performance. For all the summaries, I will keep the final and trace data summaries separate, given the different data sources. The results indicate that for the final volumes, students appear to have done very well at recording these values. Where we see the most difficulty, though, is in the trace data, where students are not getting less error-prone as quickly on the burette trials as they did on the graduated cylinder trials. Next, we consider the second learning performance. This learning performance concerns whether students' measurements were accurate and precise. We will first look at the accuracy component in Evidence Statement 2.1. When looking at the accepted volumes that students reported for graduated cylinder trials, around 60% of students had a value in the range of 0 to 10 milliliters. Then if we look at the accuracy of all attempts made in the trace data for graduated cylinders, we can similarly see that 56% of students had all volume attempts in the range of the glassware. The second component of this evidence statement identified that the spread, or distance from min to max, in a student's trace of data entry attempts should decrease. We can see here that 86% of students did exhibit a decreasing spread across all experimental trials. Next, we consider the accuracy of the accepted volumes for burette trials. Here we can see that around 90% of students entered a value in the range of a 50 milliliter burette for all experimental trials. The trace of data entry attempts for burette trials show that, again, around 90% of students had an attempt in the range of the glassware. Trace data also indicate that the spread of attempts made with the burette also declined like the graduated cylinder. 70% of students exhibited a decreasing spread in their attempts across all trials. So then, looking at the Evidence Statement 2.1 concerning the accuracy component of Learning Performance 2, students were better able to record volume measures in the range of burettes than for graduated cylinders, though the trace data indicates that burette attempt spreads were a bit more choppy across trials. So this data, when including the analysis of trace data, puts students at more of an even footing for the two types of glassware. The second evidence statement in Learning Performance 2 concerns the precision of the values that students entered. When looking at whether students' accepted values were specified to the correct precision, we can see that 100% of students attained this criteria. Again, this should be unsurprising given that values are only accepted after passing procedure-specific validation criteria in Labflow. The trace of data entry attempts for both types of glassware indicate that students struggled noticeably at reporting volumes to the correct precision for all trials. Only a third of students reported all graduated cylinder measures to the correct number of decimal places, and only about half of students did the same for burettes. The second evidence statement for Learning Performance 2 also specifies that students should make fewer precision modifications in their trace data entry attempts. The data indicate that greater than 90% of students decreased the number of precision modifications they made across all experimental trials. So then, looking at Evidence Statement 2.2 concerning the precision component of Learning Performance 2, we can see that in general, while it appears students understood precision well from their accepted volume measures, trace data show that students struggled while entering precise values, especially for graduated cylinders. This may reflect the observation we made that they become less error-prone as they progressed through the experiment. Then finally, we can assess the extent to which students attained each learning performance. Again, the data are presented separately based on the final accepted values versus the trace data. In general, what this analysis suggests is that students struggled more with entering volume values for the burette compared to the graduated cylinder. However, when it came to accuracy and precision, fewer students hit the benchmarks for these skills overall, and graduated cylinders appear to have been more difficult to use accurately in this procedure. If we then revisit the research question driving this project, we find that learning performances and evidence statements can indeed be applied to large-scale data. The lab skill of accurately reading glassware was defined as a number of component subskills: recording valid numeric data, recording volume measurements within the range of the instrument, and also making sure that they match the precision of that instrument. We found that trace data and final data could be analyzed using similar competency thresholds. Interestingly, though, trace data highlighted novel error patterns that were not present in final data alone. These error reduction patterns serve to separate students qualitatively by the path they took through data entry. Thank you for your time. If you are interested in doing research in the laboratory education space and would like to know more about the big data capabilities of Labflow for researchers, please reach out to us at research@catalystedu.com or visit our website at catalystedu.com/Labflow. If you're interested in knowing more about our OER library, please visit catalystedu.com/experiments.